Okay, so yesterday we introduced the idea of what an exponential function is. We were talking about those functions that have a base that's just a normal number, 2 or 1/3 or something like that, and the actual variable part is in the exponent, which is something new that I don't think we've really had before. So an exponential equation, something a little bit different. It's not a function. It's not something that you graph. It's an equation, much like the one that you can see down here, that involves variables in the exponent. Okay, so in an exponential equation, it is an equation in which variables occur as exponents. Okay, so the biggest thing to keep straight when we're talking about, like yesterday we were talking about functions and we were graphing functions. Typically functions are graphed and typically equations are solved. So normally when you see something about like, oh, this is an exponential equation, typically you're going to be solving it. Functions usually have like an f of x or a g of x or even a y, and your end goal is to graph them. Today we're dealing with equations and our goal is to solve them. All right, so we've got this property. It's a property of equality for exponential functions or exponential equations, either way. So we start off with this. Let's say, let b be greater than 0. So we know the base has to be something positive. We talked about that a little bit yesterday. And the base can't be equal to 1. If the base were equal to 1, it wouldn't be an exponential equation, because if you raise 1 to any power, you still just get 1. Okay, so we start with that. Those are kind of like our conditions of this statement. So then here's the actual property. Then b to the x is equal to b to the y if and only if, and I'll explain that in a second too, x is equal to y. So you guys know if-then statements, how those work. If and only if statements go back and forth. So if and only if means if this is true, then this is true. And also, if this is true, then this is true. So it kind of goes back and forth. So you could say if x equals y, then b to the x equals b to the y. So if you know this is true, then you automatically know this is true. But it also says if you know that this is true, you can conclude that this is true, which is the more important direction, I guess, for what we're doing today. So we're going to use this property of inequality to solve these equations. So we know that if we have the same base raised to different powers, we can just set their powers equal to each other. So if you're looking at something like example A, sure, it doesn't look like it fits this property of equality, but our main way to solve these is by rewriting one of the sides as a power of this variable over here. All right, so 4 is going to be our base, and then we write 2n minus 1, that's what our power is. Now 64, and this is super, super important that we start to memorize some of these powers that I've talked about in the last chapter. If you don't know that 64 is a power on 4, you're not going to be able to solve this equation. So it's very, very important to know some of those powers. So 64 is actually 4 to the third power. So that's our main technique that we use with these equations. So like I said, it's absolutely essential that you know that 64 is 4 to the third. If you don't know that, you won't go any farther than this original equation. So once we get this, kind of transfers into this property of equality right here. If the same base with different powers, if we know these two sides are equal, which we know they're equal because that's the equation that was given to us, we know that their powers must be equal. So x and y are the powers, we know they must be equal. So we can just say that 2n minus 1 must be equal to 3. Based on that property that we have up above, and then we just solve. Okay, so we end up with n equals 2. So that was the first one. We've got another one, part B. Part B is very, very similar. So we've got 5 raised to the power of 5x. And then on the other side, we have 125 raised to the power of x plus 2. So the first step is always to get them written with the same base. So 5 can't be written any differently, so we're going to leave it as 5 to the 5x. And then 125 is 5 to the third power. So again, if you do not know that, then you won't get any farther in this problem. So it is super important that we know some of those exponents that I had you guys write down in the review video. And then we have x plus 2 on the outside, okay? So here's something that's super important. The 3 is attached to the power right here. Remember one of our properties of exponents that says if you raise a power to another power, you multiply the powers together? So the right-hand side is actually 5 to the, and then we multiply 3 by the quantity x plus 2, which means we actually end up distributing the 3. So it should look like that. Okay, so be very careful with that. It's very easy to just make it 3x plus 2, but that wouldn't be right. You have to distribute the 3. So now that our bases are the same, we can use the property of equality and just set their powers equal to each other. Okay, and then just solve that teeny little algebraic equation. Okay, so these would be pretty easy to check if you plug them back in. If we plugged in 3, 5 to the 5 times 3, that would be 5 to the 15th power, which is really, really big. If we plugged it in here, 125 to the 5th power. So 5 to the 15th compared to 125 to the 5th, you could check and show that that does, in fact, give you the same number. All right, so just some equations to solve there. We're going to look at some of these ways that you apply exponential equations. So yes, they are story problem type of problems that we'll be working on here. We're going to use info about this growth or decay that we've been talking about to write the equation of an exponential function. Okay, so this example says a manufacturer distributed 3.2 million aluminum cans in 2005. That's kind of our introductory little bit of info here. So starting with part A, in 2010, the manufacturer distributed 420,000 cans made from the recycled cans it had previously distributed. Assuming the recycling rate continues, write an equation to model the distribution each year of cans that are made from recycled aluminum. Okay, so we are going to come up with an equation, and for some reason I didn't leave you any room there. So we know that our exponential function is going to be y equals a times b to the x. It's like our very generic exponential equation. So this is something that's going to be important in the work that we'll be doing in class. So we start with our points that they gave us. They gave us an initial point. So let's just consider this to be our initial, like this will be x equals 0. That'll be our starting point in 2005. And then in 2010, that's 5 years later. So we'll say that's x equals 5. So we have two ordered pairs. All right, so in year 0, there were 3.2 million cans. So 3.2 million. And then, actually we should probably do millions. Sorry. Yeah, let's write it like that. And then the next one is this right here. So in year 5, we had 420,000 cans. So we are going to use these 2 points right here, and we're going to find our exponential function. Okay, so the first thing we're going to do is we're going to plug this point into this equation right here. So you replace the y with 3.2 million. We don't know what a is. We're trying to solve for it. We don't know what b is. We're trying to solve for that too. But we know that x is 0. All right, so let's start to simplify this up. So b to the 0 is just 1. And so this tells us that a is equal to 3.2 million. Because it's really just a times 1, and so that must mean it's equal to the left-hand side here. So next, we replace the a in our equation right here, and then plug in the next point. So we're plugging in 420,000 for y, equals, and then we're plugging in 3.2 million for a. We still don't know what b is. That's what we're going to try to solve for. And then we know that our exponent is 5, because x is 5, so we're plugging it in right here to this equation. Okay, so we are first going to divide by 3.2 million. Okay, so it cancels out right there. And then let's see what this ends up being. Okay, so we've got 420,000 divided by 3.2 million. Gives us 21 over 160. equals b to the fifth. All right, so what we're going to do to get b by itself is take the fifth root of both sides. All right, so to do that, our fifth root is over here, a couple over from the 4, so you have to hit control first to get a different index. So we're going to take the fifth roots of 21 divided by 160. Okay, so we're just going to round just about 0.67. We can round to 2 decimal places. So b equals about 0.67. Okay, so we've got a, we've got b. We are going to turn that into an equation. So y equals a is 3.2 million. And then times our base. And then we plug our variable back in, which is x. All right, so that's part A. We came up with an equation, 3.2 million and then times 0.6 to the x. And then let's sneak in part B, and then our definition will just come down here. How many cans made from aluminum recycled can be expected in the year 2050? All right, so if we consider 2005 to be year 0, then 2050 is 45 years later. So for part B, we want to plug in x equals 45. All right, so we're going into this equation right here, and we're just going to plug in x equals 45. So y is going to equal 3.2 million, and then times 0.67 raised to the 45th power. Okay, and I will show you how to plug that in. So we do 3.2 million times 0.67, make sure that's always in parentheses, and then raised to the 45th power. Okay, so about 0.0477. Okay, so what we ended up with is 0.0477 cans. You're not going to see 0.0477 cans. You're not going to have any. So the answer would actually be none. So it gets to the point where after a certain number of years, like in 5 years, they went from 3.2 million down to 420,000. It's shrinking pretty quickly. And so apparently after 45 years, it shrunk so fast that there are none left. So you would just end up with none. You're not going to have 0.05 cans. That's barely even a real number. Okay, so let's do this compound interest definition really quickly, and then we've got one more problem. So compound interest, you guys may have heard of this, especially if you've done econ or anything like that. So compound interest has a formula that looks like this. A equals, we've got P, and then in parentheses, 1 plus R over N, and then outside the parentheses, the power is N times T. Okay, so I'm going to use a different color and kind of label what all the different things mean. Okay, so P. P stands for principal amounts. P stands for principal amount. That's how much you invested. If you put $1,000 into an account, P would be 1,000. R is the rates. You guys have probably heard of interest rates before. If you're at like a 6% interest rate, you'd use 0.06 for the rates. N is the number of compounding periods. Number of compounding periods per year. So if you compound it every month, in a year you would have 12 compounding periods. If you compound it every week, in a year you would have 52 compounding periods. Hopefully that makes sense. T is the amount of time. And it's always going to be in years since we started talking about years here. And then finally, A is the amount that you have after T years. And then this N up here is the same thing as this N. All right, so we've got all those things in the formula. All right, so finally, let's answer this last example, example 3. Find the account balance after 20 years. Okay, so 20 is T. If $100 is placed in an account, so that must be the principal amount, that pays 1.2% interest. So that's the rate, except remember, since this is a percentage, you do it in decimal form, which would look like that. And compounded twice a month. So twice a month, there are 12 months, and if you go twice a month, then that means you're going 24 times in a year. Okay, so we've got all of these things. We're just going to put it right up into this formula. So A equals the principal amount times 1 plus R, the rate is 0.012, and then divided by the number of compoundings, which is 24, and then our exponent is 24 times a year times 20 years. All right, so this is going to tell us how much we're going to end up with. Okay, so we'll plug this in, so you've got the 100, and then parentheses 1 plus, I would make sure you do a fraction for this next part, 0.012 divided by 24, and then a little exponent, you do 24 times 20. Okay, $127 and about 12 cents. Not all that exciting. That is a very low interest rate, and you didn't put very much in to begin with. I would be very sad to come back 20 years later and find that I only had $27 worth of interest, but oh well. All right, so we are actually cutting here for now. We're going to do a second half with exponential inequalities in the next lesson.